Okay, let's look at this one. Step number one, okay, we want to actually know what's our titrant, what's our analyte. So in this case, our titrant is sodium hydroxide, 0.1 m. Our analyte is CH3COOH. It's also 0.1 n, but you have 100 ml of this guy. And then it has a Ka of 1.76 times 10 to the negative 5. Step number two is we want to actually write out the ionic equation. We know for the strong base, you are going to have sodium hydroxide. Sodium hydroxide is Na plus OH minus. It's going to dissociate 100%. Okay, so that will be actually the species you're going to have inside your solution. And then it's going to interact with your weak acid. So the key here is actually you can just write out your weak acid directly because the weak acid doesn't dissociate much. So majority of the weak acid existing in the acid form. So these two, once they interact, the base is going to interact with your weak acid. So that you're going to have CH3COO minus. Okay, so you're going to produce its conjugated base N2O. Inside your solution, you still have sodium plus remains. So let's actually complete ionic equation. But the most useful one is actually the net ionic equation, right? Which will be, this cancels out, okay? All you have is actually OH minus plus CH3 COOH. That give you CH3 COO minus and the H2O. So in general, okay, every time, this is actually a very specific case, right? But I would suggest that you see these things as just a strong base, OH minus, interact with your weak acid, HA, that give you A minus and the H2O. So that you know, all you have is actually a weak acid, strong base, titration condition. Step number three is actually you want to calculate your VEP, right? The equivalence point of this titration. And then the concept you are going to use is number of mole of your titrant is going to equal to number of mole of your analyte. And the way you calculate the number of mole of titrant or analyte is actually using the concentration of your titrant times the volume of your titrant. It should equal to the concentration of your analyte times the volume of your analyte. The volume of titrant will actually equals to your VEP. This can be written as concentration of your titrant times your VEP is going to equal to concentration of your analyte times your volume of your analyte. So concentration of your titrant, which is actually the concentration of NaOH. So in this case will be 0.1 m. The volume is actually the things you're actually looking for. You want to know how much should I add into my flask so that I can reach my equivalence point. Concentration of your analyte is also 0.1 m for your acetic acid. Volume of your analyte is 100 ml. So from here, we can clearly see the VEP is going to equal to 100 ml, right? If I plot out my pH versus titrant volume, I know at 100 ml, I'm going to see my VEP. And then I know I have a weak acid to start with, right? If that's actually a pH 7, I know I should start somewhere below and then gradually goes up and then doing something like this. After this, we're going to calculate pH at 4 different zones. So let's start with zone number 1. So right now we know we have 0.1 m, 100 ml acetic acid, which is a weak acid solution. The analyte we have is CH3COOH. Concentration is 0.1 n. We have 100 ml. Ka is 1.76 times 10 to the negative 5. So we know it is a weak acid. Okay, therefore the proton concentration can be calculated from the square root of the acid concentration times your Ka. Therefore, we know the proton concentration is going to equal to the square root HA concentration is 0.1 m. Ka is 1.76 times 10 to the negative 5. You should see a value of 1.33 times 10 to the negative third. Okay, so that's actually your proton concentration. pH, negative log, proton concentration, which is going to equal to negative log 1.33 times 10 to the negative third. Therefore, the pH is going to give you a value of 2.87. Okay, so we are going back to the zone 2 later, okay? But I want to calculate the zone 3 first. Okay, so let's look at zone number 3. Here, let's write out our net ion equation, which is actually the strong base is going to interact with your weak acid. That gives you the conjugate base plus H2O. At zone number 3, we know it's actually an equivalence point, right? Therefore, you have the same amount of OH minus and HA. They're going to consume with each other and produce your A minus. Okay, and then we know the pH was simply determined by your A minus, which is a weak base solution, right? So all you need to do is actually, you know, in the beginning you have, okay, I probably need to do the ice table here so you'll see more clear. In the beginning you have 0.1 m of strong base. You have 100 ml to reach the equivalence point. You are going to have the same amount of your weak acid. And these two is going to consume with each other, right? So you know you're going to have minus 0.1 times 100, minus 0.1 times 100. At the same time, you're going to have plus 0.1 times 100 for your A minus, and then plus 0.1 times 100 for your water. At equilibrium, you don't have any OH minus, you don't have any HA. All you have is actually 0.1 m times 100 ml, that much more of your A minus, and then the same amount of water. But we know this is actually the species that's going to contribute to your pH. So all we need to do is actually we want to calculate the final A minus concentration at equilibrium. Okay, we're going to calculate through the number of mole of my A minus divided by my total volume here. Okay, so this step is actually very important because that's how you calculate the A minus concentration. Okay, so here you know the number of mole is actually 0.1 times 100 ml, right? Total volume right now is actually, you need to consider the volume from your titrant, also the volume from analyte. So you know the volume of your titrant is 100 ml. Volume of your analyte is also 100 ml. Okay, so this is actually the things that's going to be changed. Therefore, if you do these calculations, you're going to get a concentration of 0.05 N. So you know that's your base concentration, right? So you have weak base solution with a 0.05 M concentration. Therefore, you know you can calculate your OH minus concentration is going to equal to the square root of your A minus concentration at equilibrium times your Kb. A minus concentration is 0.05. But do we have Kb? We don't. So to actually recalculate your Kb, the way you calculate your Kb is that we know Ka times your Kb is going to equal 10 to the negative 14. And then here we know your Ka is 1.76 times 10 to the negative 5. So you can calculate your Kb going to equals to 10 to the negative 14 divided by your Ka. Then once you get the value, you're going to put it here. Okay, then you can calculate your OH minus concentration, which is going to give you a value of 5.33 times 10 to the negative 6. Once you have your OH minus concentration, you can calculate the POH, which equals to negative log of your OH minus concentration, which is equal to negative log of 5.33 times 10 to the negative 6. And you are going to get a value of 5.22. So your POH is going to equal to this. Okay, therefore you know your pH is simply 14 minus your POH. Okay, so therefore your pH is going to equals to 8.78. Okay, so let's actually how you calculate the pH of zone 3. Zone number 4. So zone number 4, we know all we have is actually the remaining thing is actually inside your solution is actually your strong base, right? So all you need to calculate is actually what is the concentration of my strong base in this solution. Then I can know my OH minus concentration. Therefore, I can know my POH. Therefore, my pH. So what is the excess amount of your NaOH? So you can still use this equation to do all this calculation. Okay, OH minus plus your HA, that give you A minus plus H2O. Okay, so in the beginning, you have 0.1 m times 100, right now it's actually 100.05, right? That's for your OH minus. For your HA is 0.1 times 100. So at this time, this will be the limiting reagents, right? So your weak acid will be fully consumed by your titrant. Okay, therefore we know that is actually the thing that's going to be fully consumed. Okay, so you're going to have minus 0.1 times 100 here. You're going to have plus 0.1 times 100 here. Okay, so once you reach equilibrium, all you have is actually 0.1 times 0.05. This is 0, then you have 0.1 times 100 for your A minus. So right now you are going to have OH minus and the A minus coexisting inside your solutions, right? So OH minus will be actually the species that determine your pH. Okay, because this is actually a strong base. Okay, so you know this guy is actually the species that's going to determine your pH. So we want to calculate the OH minus concentration then. So again, what we do is actually the number of mole of my OH minus divided by the V total. Okay, so here we know number of mole is actually 0.1 times 0.05. V total is actually 100.05 plus 100. So when you do these things, then you can get the concentration equals to 0.0476. So let's actually your OH minus concentration. So from there, you can get your POH is going to equal to negative log OH minus equals to negative log 0.0476. You're going to get a value of 2.32. Therefore, the pH simply equals to 14 minus 2.32. That gives you 11.68. So let's how you calculate pH at zone 4. Now we need to come to the zone 2. In zone 2, we know we are going to have a buffer solution. I want to change these things a little bit, okay? So on the slide, I actually shows we add in 30 mil, right? So I want to change it to 50 mil for now. Okay, so let's say we add in 50 mil. Okay, 50 mil of NaOH. So in this case, if you do these things again, okay, OH minus plus your HA, they give you A minus plus H2O. And then in the beginning, you have 0.1 m times 100 mil, that much HA, right? And I add in 0.1 n times 50 mil of OH minus. The limiting reagent is actually your titrant, which is the OH minus. This guy will be fully consumed by that guy. Okay, so I'm going to minus 0.1 times 50 minus 0.1 times 50. I'm going to produce 0.1 times 50 of my A minus and then H2O. Then I'm going to reach the new equilibrium where the OH minus concentration will be 0. So your HA will be 0.1 times 50. You have that much of HA. You have 0.1 times 50, that much A minus. You have 0.1 times 50, that much H2O. All right, then we want to calculate pH of these things, right? So from here, you should see that your HA has a number of moles 0.1 times 50. Your A minus also have 0.1 times 50, right? So we know this is actually a buffer solution where the acid concentration, HA should equals to number of moles is actually 0.1 times 50. Total volume is actually 50 times 100. Okay, so the concentration of your HA is 0.33. If you calculate your A minus concentration, number of mole again is 0.1 times 50. Final volume is actually 50 plus 100. They also give you a concentration of 0.33. Okay, then we want to calculate the pH of a buffer, right? So we use HH equation, where the pH is going to equals to pKa minus log acid HA over your A minus. pKa basically is actually a negative log of your Ka. Ka is 1.76 times 10 to the negative 5. Negative log acid concentration is 0.33. Base concentration is actually 0.33 as well. Therefore, the pH will equals to 4.75.